Hey everyone, let's get started here. We'll see if anyone's in the chat. I know I just started these office hours, but I'm hoping to get... there we go. We got that going. Got this going. Start the chat. Hear myself in the background. Top chat, live chat, top chat, pop out chat. Reactions. There we go. There we go. Sit up straight. Got things on my shoulder. Get on my shoulder. Okay, this is all wrong. Got Monster Energy today. Need it. Had to get up early this morning, go to the dentist. Nice clean teeth. There we go. No cavities. We like that. We are good to go. Let's start talking about the confidence intervals assignment. We can get this done here during office hours. People can watch it later. And let's go do it. Okay, we need to take the notes right here and talk about the confidence interval assignment. So this is at the 204 mark. Stat 201. Chapter 13, MyPearson, homework, confidence intervals. Q1. Okay, this first one right here deals with confidence intervals, and it wants us to talk about what the interval means. So they're asking teenagers, how often do you use the internet? Well, 45% said they're online several times a day. I think that's much higher these days. It's 90%. And then we make an interval right here. Now, notice the interval goes from 42 to 48%. Whenever you get a confidence interval, you want to realize the components of it. A confidence interval has a few components. Let's break them down. It has an estimate, and then has plus or minus the margin of error. Now, we'll break these down into more parts later, but that's the basics of a confidence interval. So they estimate 45% of teenagers are online constantly, plus or minus 3%. And what this will do is this will create a lower estimate and an upper estimate. You simply add and subtract these numbers. So there it is. We are pretty sure that probably somewhere between 42 to 48% of teenagers are online constantly. And that's what we have right there. I think there's a note. Yeah, it's sugar-free. It says sugar-free. Tastes like sugar, so that's sucralose. So what does this mean? I am 95% confident that if we were to ask all the teenagers, that's somewhere between 42 to 48%. Mubot's also got the interpretation of a confidence interval in the chat. If we say confidence, he will put it in the chat where we say I am blank percent confident that the true blank is contained in the interval blank to blank. So I am 95% confident that the true proportion of teenagers who are online constantly is contained in the interval 42 to 48%. This is some of the interpretation you need for test 3. Explain what 95% confident means. This actually goes to, let's go to seeing theory. Confidence intervals. I'll show this tomorrow probably. But here we go. That's not it. If I can't find it, then we won't be able to do it. Okay, here we go. Confidence intervals. So there's a page called Seeing Theory right here. And what you're going to see is a confidence interval. If it does the things right, let's select from the normal. And we're going to create 95% confidence intervals. Here we go, 95%. If you make a 95% confidence interval, then the truth, sure, 96. Mu is the truth, and 96% of the intervals will contain the truth. These intervals in green right here have the truth inside of it. If we get a red interval, notice the bands up. See, that one doesn't contain the truth. And we're taking random samples of size 5 from a population right here. This is what we're sampling from. It says sample up there, but this is where the sample is coming from. The samples are the dots coming from the population. So it creates a sample of 5 observations, which creates an interval. And if the interval has more variation, notice how that dot's a little bit closer together. If they're more spread out, there'll be a wider interval. Now, it doesn't just go to the length of the interval. There's more calculations than just the highest and lowest value. See that interval right there does not contain the truth. And what you'll see is we have about 6% don't contain the truth and 94% do. Oops, I accidentally hit enter right there, spacebar, and it, oh, no, it's still going good. Thought we lost it. But if I change the screen size, it does. What you'll notice is if we keep this simulation going, I'm going to try to make it, well, that was weird. I can't get it to zoom in really well. It's going to be very tiny. Ooh, 4%, which 96%. This is the law of large numbers coming into play right here, that if you were to make intervals 96% of 96% confidence intervals are contain the truth, you would expect most of them to contain the truth. Just around 4% are not going to contain the truth for 96% confidence. So in the long run repeated of making intervals, if you make intervals, 95% of 95% confidence contains truth. Hey, DD, good to see you there. Just saw you in the chat. This is a cool site called Seeing Theory. And look, intervals could just not contain the truth randomly. So it's a really cool site. So there's about a 95% chance that the true proportion, if one were to collect many random samples, about 95% of the confidence one would construct would contain the truth. That sounds right there. I think so. Let's see, check answer. Oh, that's the other one. I should have read a little bit more. Oh, of size. Okay. So they're being very specific right here because they're saying of this size. Just show that again here real quick. They're being very specific in going of the size that we created. It's a fact, though. 95% of 95% confidence contain the truth 95% of the time. It's over the long run of creating these intervals. It's not that one interval has a 95% probability. It's that the long run creation of intervals, in the long run, 95% of your intervals. Wait, can you leave it on the screen? Which, this right here? Or the seeing theory thing? Yeah, so right here, it's not that one interval contains the truth 95% of the time. Because one interval either contains the truth or doesn't contain the truth. If you create a bunch of intervals, then a bunch of intervals over the long run, it goes to the law of large numbers, which the law of large numbers states, I'm going to do law of large numbers. If you look at any law of large numbers graphics, it shows you how over the long run, you're going to see the true probability of something. So it's not about creating one interval and it contain the truth. It's that over the long run of creating multiple intervals, 95% of 95% confidence will contain the truth. And one interval either will or won't contain the truth. Good questions. So basically, many in A. Yeah, it's just that they didn't mention the size. It's a little ridiculous. It caught me. It shouldn't have caught me. But they want us to talk specifically to the size because that'll dictate the standard error in the equation. So they're getting very specific right there. So one is 95% confident that the truth for the full population is contained in the interval. And then if we were to make a bunch of intervals of this same sample size, about 95% of those intervals would contain the truth. 95% of 95% confidence contain the truth. This one's really cool right here, and this deals with the empirical rule. So, DD, do you know the empirical rule, the 68, 95? Thank you for being here. Yeah, let's practice some stats. 68, 95, 99.7. Do you know how that works? The 68, 95, 99.7 rule. Yes. So if we were reaching out two standard errors, 68, 95, this will make about a what percent confidence interval? It'll make a 95. So that's literally the 68, 95, 99.7 rule. And I do want to mention this. If we want the exact z-scores, people use a z-table 60. Yep, one standard error would be 68. And if we want the exact numbers right here, we're going to go over here to our applet, and we're going to click the between button. If you click between and you see 95, it's actually 1.96, where 68 is basically 1. It's actually 68.26, 95.449 is 2, and 99.73 is 3. So usually what we do is someone says, I want to make a 90% confidence interval, and the z-score is 1.6449. And if we do the more decimals, we'll get those numbers. That's standard deviation. I don't want to change that. But it's 1.6449 right there. I usually do to 4 decimals just to carry everything. Someone says I want to make a 98% confidence interval. That's 2.3263. And there's the values right there. And as you get more confident, the z-score gets bigger. So just to show you what that is, in the equation I mentioned there's an estimate and a margin of error. Well, right now, we're trying to estimate P. So our best guess of P is the sample proportion. And the margin of error is a z-score, which tells us how confident we are, times p hat q hat over n. And this quantity right here is called, that's too huge, the standard, still too huge, the standard error of p hat. So that quantity is called the standard error of p hat. That is p hat times q hat over n square root, that quantity as a whole. And z gives us the level of confidence. Everything inside of here is the margin of error. So this is all margin of error. Like everything there, all margin of error. Everything after the plus or minus is margin of error. Important stuff to know. Yeah. Well, ask the question. Because how confident we are controls the z-score. Yeah, keep out. I don't. Which question is it? Did I miss it? So 95% confidence interval is basically 2 standard errors, technically 1.96. But you can tell me what P, Q, and N are? Yeah. So in notation, so P is true proportion. Like if you think about the percent of students that are actually in state, that's the true proportion. Q is complement of P, which is 1 minus P. And then P hat, we have to insert it here, is sample proportion. P hat is sample proportion. So sample proportion is like you talk to 100 students and 20 of them are in state. So that's the sample proportion, 20 over 100. So P hat is the estimate of the truth. So this is sample proportion. And then Q hat is complement of sample proportion, which is 1 minus P hat. So we usually, when we do statistics, we only know the sample values. We don't know the truth, because the truth is like the actual proportion, like how many people are actually in state. Hey, Brando, what's up? And complement of sample proportion. So then it's just 1 minus P hat is Q hat. Brando getting those mu bucks and those points. There we go, right there. And then N is lowercase n, sample size. Very important things to know right here. Yeah, so we want to know what percent of students, let's say what percent of students will get into law school. Now, we don't know from UT the truth, but and the equation super quick. Yeah. So the way it would work in a question, let's do an example question right here. We want to know the true proportion of, so that'd be P, of UT students who get into law school. So I'll disappear. We talk to 200 students who applied, and from the 200, there were 40 who got in. Make a 95% confidence interval. So we want to know, we don't have all the data. We want to know the true proportion of students who get into law school. Does that make sense? Just theoretically. And then our best estimate, we're going to use our sample right here. And then we need to get the P hat. So P hat is equal to X over N. X is the amount who applied, got in, over the sample size. So this is going to be equal to 40 over 200. So does this make sense? In our sample, guava Monster Energy. I shouldn't be drinking it. Guava Monster Energy. I got up early today. I need this Monster Energy. I don't want this Monster Energy. I need this Monster Energy. So 20% of the sample got in. So what you do is you then go down here and you take your estimate, which is your best guess of the truth or rebel. Yep. Then you choose how confident you want to be. And then you plug in the rest of the equation, the standard error. So that's the standard error right here. This is estimate plus or minus the confidence level times the standard error. Standard error is a metric of variation. It helps us know how variable the estimate is. So now we plug in the values. So this is going to equal to 20% plus or minus, and we're going to use 1.96. And that's because our confidence is going to be 95% confidence. If we plug in 95% confidence, the z-score is 1.96, and we cover 95% of the area. So that's why we're choosing this for 95% confidence. That's linked to that number there. There's a star because that means you pick it based on confidence. And then we plug in 0.2 times 0.8 over the 200. And now we just simply solve the equation. And we go over here. We do 0.2 times 0.8 divided by 200 and square root. And that's the standard error times 1.96. And we get about 5.5. So, yep. So what we get right here is 0.20 plus or minus 0.55. And this is going to create an interval that says somewhere between about 0.145 through 0.255. And the way we would do this, thank you. So I am 95% confident the true proportion of students who get into law school is somewhere between 14.5 to 25.5%. Like somewhere between like what percent of UT students get into law school? Well, somewhere between 14.5 to 25.5 of the students who apply get into law school. So we don't know. We don't know what the truth is because we don't know all the data, but this is our estimate of what the truth might be. Like we think the truth P might be contained in this interval because we don't know what the truth is. We only have an estimate. Thank you. And that's really good right there. That's why we make confidence intervals to estimate what the truth might be. Some of these are pretty easy, especially if you know the formulas. Let's do this next one. Got a little bit of time. Got like 12 minutes. Let's do it. I like those questions. Yes, well, not the normal, the T distribution by Gennesbeer, William Seeley Gossett, which is a test question on test 3 sometimes. The normal curve was created by Gauss, Gaussian curve on the Deutschmark. Good question/answers. Make sure to know that. The T curve created by William Seeley Gossett at Gennesbeer around 1910 or so. So that's always the T curve, which is a variation on the normal curve, which comes up in the next chapter. A morning poll right here. It wants us to calculate the margin of error right here. So this really boils down to the notation. So everything we just did there, DD, this is going to be a notation problem. Notice how it says 99% confident. Since it says 99% confident, that's going to dictate the z-score. Now we know that this is, they want a proportion for the thing we're on the wrong track. So that makes this p hat, and that makes this q hat. And they're p hat and q hat because this comes from a sample right here. This isn't the truth, it comes from a sample. The z-score for this is 2.5758. And the reason I know this is because I've memorized them. You'd have to go here to the apps, which is on the screen now. The mathematicians do like to drink, apparently. And when you go here to the apps, you want to go between and go to 99%. There it is right there. The T-curve can be found right over here. There's William Seeley Gossett's T-curve, known as the student T, which was a pseudonym he used when he published in Biometrica back in like 1910 or so. And so now we just plug into the equation. So let's do it. Okay, we go P, we shake the screen. That's what we do. We go P hat plus or minus the z-score times the standard error. The standard error is P hat times Q hat over N square root. So we plug into this 0.747. It actually just wants the margin of error, so we can just solve the margin of error. It only wants this last component because it said, what is the margin of error? So we're only putting in that. Now we have to times this by Q hat. And then we divide. And 1997. Okay. Let's solve this out, the margin of error. We're just solving this portion I've circled right there. And so 747 times 253 divided by 1997. Square root, do not forget the square root. I've done this many times. 2.5758. And there's the margin of error right there. Let's bring it back over here. 3 decimals, and we've solved it. There we go. What does it mean? The margin of error tells us that it's kind of a plus or minus on the interval. One is 95% confident. The observed proportion is this close to the truth. I don't love the way they're phrasing it right here. It's about how far we could be away from the truth. That question, the margin of error is, yeah, it's about how far we could be away from the truth, but they could have phrased it a little bit better. Let's try to do, I don't know if we can do all these. Let's try, because we're running low on time. Sorry, I got started so late. It's an early morning, getting my teeth cleaned. Get teeth cleaned early morning. Okay, question 4. This boils down to notation. All this question is knowing your notation. So notice the first thing we do when we start any question.
Notation, brother.
Notation. Every question for the remainder of the semester is pretty much knowing notation. We talked to this many people, sample size. This percent said something we liked, that would be P hat. Once you find P hat, you instantaneously find Q hat. Q hat is just the complement. And River, does this help right here? DD, sorry. Sorry, names in my head. DD, does this help right here? that just the practice right there, p hat and q hat, yeah, they're complements, and it's the percent we saw. Rivers, okay, thank you. It's the percent we saw from the sample right there, and I think that's mostly got it. Yeah, exactly. Oh, I didn't know that. Maybe I knew that. I think I kind of knew that. And then 95% is related to the z-score. It explains how far out we go on the curve to cover 95% of possible values. And the z-score for this is equal to 1.96. Once again, on the test, we would give you these. And so we'd go over here and we'd enter in 95% confidence. And there's 1.96. On the test, we'd give you that. It's basically 2 from the 68, 95, 99.7 rule. The more standard deviations or standard errors you go out, the more area you cover on the curve. So what do we do to get the intervals lower and the upper? Brando, great job there too. Let me throw you some points, everybody. Mubot's in the chat. We're just going to go here and go to p hat plus or minus z square root p hat q hat over n. And then we go right here and enter in p hat 5.16 plus or minus the z, which is 1.96 square root point, good, I'm not covering yet, 516 times 0.484. And then we go right here and divide by this sample size, 4527. And we solve. 0.516 times 484 divided by 4527 square root and times by 1.96. There's the standard error. So that's about 0.15. So and yeah, so this is going to be, we get the lower and the upper from this. We just try, I guess the confidence interval would be really huge. It can be, is there a different rule to follow when n is less than 100? You're right. For smaller sample size, it creates larger margins of error. That's actually very, because think then you have less data, so you have less understanding, so your interval is going to be wider. And it can actually run into problems if you don't have enough successes, enough failures. Then you won't be able to use the normal curve because you might violate the success failure condition, rule number 3 for proportion intervals, or the large enough n, which is the central limit theorem. So if you have too small of a sample size, DD, if you have too small of a sample size, you can't actually use these equations because they don't theoretically work because the curve doesn't apply. So that can run into problems, but you're also right. Small sample sizes lead to large margins of error mathematically because you're dividing by a smaller denominator, making the standard error bigger, making the margin of error bigger. Good conceptual stuff. For some points in the chat. Yes, small sample sizes lead to large margins of error. Theoretically, think about it. If you have a small sample, you don't understand your data as well. Larger margin of error. Larger margin. Yeah, it's less understanding. And so we simply add and subtract. And really good comments. You're just adding and subtracting 0.1, just 0.516 plus or minus that. And did I do it right? Yeah, I did it right. 501, 531. Only once, okay. Let's hope we did it right. 501, and then 531. Ah, that's not right. Something seems off. That's right. Is that right? Let me look at the screen again. No. There we go. There we go. Okay, I am 95% confident that the true proportion of Californians who consider moving out of state is contained in the interval. This to this. I am 95% confident. So if more than 50%, well, it's above. The interval is greater than, and they're going to do something if it's greater than, so they should consider it because they're only going to do this action if it's above it. Let me just show you that again real quick, and actually might change the question, but the interval now it's still above. So what they're trying to figure out is the true proportion of people in California who are considering moving out of state. We are 90% confident, this is a different interval, that the true proportion of people who plan to move out of state is between 51.2 to 53.6. So they're going to do this action if the interval gives evidence that more than 50%. Well, the whole interval is above 50%. You think the truth is somewhere between 51.2 to 53.6. It's like if I told you, if a steak dinner is estimated to cost over $50, we should lower its price. And you estimate the steak dinner is going to be $51.20 to $53.60. That's your interval. Like, I think it's going to be somewhere between there. So because of that, should we lower the price? Well, since your whole interval is above $50, we should lower the price. We should take the action that is suggested if there's evidence that it's above 50. And this is the evidence it's above 50 because you think the true proportion is above 50. I just speed run ones right here. Let's do it. Which of these statements correctly interprets 95% confident? 95% of samples will produce confidence rolls that contain the truth 95% of the time. Oh, are the conditions met? Oh, yeah, the conditions look to be met. Random sample, large sample size, enough success failures. Oh, no. Oh, no. I'm going to speed run this, DD. The margin of error was this. Would it be smaller or larger if we did 80%? It would actually be smaller because that's a smaller confidence. So to be less confident, the proportion needs to be contained less. The margin of error would be larger. So to be less confident, the interval contains the true proportion less. Oh, so the margin of error is going to be smaller. Makes sense as I was saying it. For a given sample size, I can speedrun all these, but then I'm like, man, I want people to get something out of this because I'm not like visualizing it. Let's see right here. We have enough successes and failures. Yeah, we have at least 10 successes, at least in failures. That's good. Then make your interval. And calculate, yeah. Would you be comfortable going to Pew Research and looking up a random statistic and calculate the confidence interval from that? Yeah, you can. Mm-hmm. And they should do that. A lot of Pew Research should do that. Look at this. For a given sample size, higher confidence means smaller margin of error. That's reverse. Higher confidence means larger margin of error. So that's reverse. For a specific confidence level, larger samples provide smaller margin of error. That is true, and that's what we were saying. It's in the reverse the way you said it, River. For a fixed margin of error, larger. This one's so confusing. We've gotten a 70% on this. We've done pretty well. I'm gonna have to head off though, but you can just tell that's the interpretation right there. I am 95. We got a 75. Yep. And we've pretty much, do we get points for this? We got an 86. And then we just have to make the interval. Can I guess the interval? Okay, that is 60% plus or minus. Let's go 60% plus or minus 25%. Or 20%. 40 point. This is my guess. Check answer. How'd I do? I didn't actually solve it. Dude, not even joking. Oh, thank you. I appreciate that. Look at this guess. Come on. I wasn't even off by 100. I was off by 8,000. I was looking at the small sample size, large margin of error. I am 95% confident that the true proportion, not of the ones purchased for the study. So we'd go here and change the percentage. And I have to run with this one. What time I got to get back. Awesome. Well, we got a 90. We're going to end office hours here. Mic drop. Time to head out. Bye, everybody. Bye.